Today I will be talking about the performance and energy optimization in OpenMP applications. So I am Abdullah Shahneous Bari. I'm a PhD student from University of Houston. I'm currently doing my research under Dr. Barbara Chapman. So as we are in the OpenMP booth, let's start with what is OpenMP. I know most of us maybe know. So OpenMP usually is the de facto standard for our shared memory parallel programming. And OpenMP is mainly a thread-based parallelism. So the whole thing is given away to different threads to do the work. And two kinds of parallelism usually exist in OpenMP. One is regular parallelism, which is done by work sharing constructs. We have some constructs, and also irregular parallelism that's being done using the task-based constructs. Now, as we are going towards the exascale era, what should we do? Like, there's been a lot of talk that how can we go to the exascale era? So let's see what can be the main barrier towards the exascale era. Well, if I say it in one sentence, the main barrier will be power, power, and power. Now, because we know that DOE set a limit of 20 megawatt power limit to reach the exascale era. But as of now, we have the largest supercomputer, which is around 33 petaflop, and it consumes around 17 megawatt of power. So it's going to be a huge issue for us to reach that limit. Well, previously it used to be a problem of vendors. So as a software stack people, we didn't really care about that. Okay, they will manage the power and we will do our programming. So we need to go to the as much performance as we can get. But now there is no more freelance. We all have to chip in. As a software stack people, we have to chip in too. So what kind of solution from the software stack can we provide to get this barrier out of our way? So one of the traction that we have been getting, one of the idea that's getting a lot of traction in the HPC community is power constraint computing. The main idea behind power constraint computing is that usually you see a lot of applications, they don't really use the maximum allowed power of the processor. And as you all know, the processor is the main power hungry part of the whole system. So in that situation, what we can do is that as they are not consuming the maximum power, we can cap the power in a lower limit. In that sense, if we cap the power in the lower limit, in the same budget, we can add more nodes. And as we all know, in whole system level, if we add more nodes, we can get more performance. So this is the main idea between the power constraint computing. So there have been a lot of work done in this area. But the whole idea is that they have been mainly focusing on the whole system level performance rather than going to a power node performance. Some of the related works you can say is that Usman Sarod, Tapashia Patki, and Bari they've been done some work in this area. Well, okay, whole system level performance is coming. Now, why do we need to? Why are we here? Like, why are we in the OpenMP book? The main idea is that although in the system level performance they're getting a lot of performance improvement, but if we want to reach the maximum limit, if we want to reach the peak throughput, we have to improve the power node performance also. And we all know OpenMP is the most used intra-node programming model. So what we have to do, we have to improve the performance of OpenMP applications. Now, how do we do that? To improve the performance and energy efficiency of a certain thing, we first need to know that what are the things that actually impact these scenarios. So as of now, most of the applications in the science community is mainly based on work sharing construct. Although there are new applications that's been coming on, they are actually use task-based constructs also. So in this part, we will mainly concentrate on the work sharing part of the OpenMP. Now, what are these factors that actually impact the performance and energy optimization of work sharing constructs? First of all, how many workers are working in my work? Thread. How the work is scheduled? We can do it with scheduling policy. How much work are given to each worker at each time? We can do it with chunk sizes. Then, how the data is laid out. As we all know, the data movement cost a really big cost in terms of computing and also energy consumption. So thread affinity, using thread affinity, we can devise how the data is laid out. And at the end, well, what do the workers do when they're in the break? Like when they're waiting in the barriers, what do they do? We can control it with wait policy. So good thing about OpenMP is that we can control all these 5 parameters in the runtime using environment variables. So what we decided, so the main reason actually we came to this point is whenever we talk to different computational scientists, they said, okay, most of the time we don't really care about a lot of them. So whatever we use is that the default strategy that have been placed, we use that default strategy. So we decided, okay, can we improve the performance and also predict that, okay, for a certain parallel region, what will be the best configuration? So for that reason, we decided to carry out some experiment. In our experimental results, we selected different parameters, number of threads, different level of number of threads, different scheduling policy, different chunk sizes, wait policy, and also thread affinity. And the thing is, as we were saying that power constraint computing, a certain node will be under a certain power cap. So what we did is that we tried this configuration selection on 5 different power cap levels. And for power capping and energy measurement, we used RAPL, and for the kernel level measurement, we used the recent OpenMP De. We tried our experiments on next parallel benchmark. So let's see how it did. You'll be surprised. So this is the comparison of default strategy compared to the best possible strategy for a certain parallel region. So 0 is just the default strategy, and the performance improvement, all you can see is the strategy that's not a default strategy. So you can see that a configuration selection can improve the performance up to 90%, and you can see that in all this, in 40 kernels, 30 of them actually has got performance improvement more than 20%, choosing the best configuration. Now we decided, okay, we're getting performance improvement. That's really good. Okay, can we do anything about energy improvement or not? So then we went again and choose the configuration that saves a lot of energy too. Here's the results. As you can see here also that compared to the default strategy, choosing the best possible strategy actually gives a lot of energy improvement too. After that, we decided, okay, we are getting a lot of energy improvement, and so one of the main important thing is that I talked in the beginning is that in the different power cap level that a certain application doesn't really reach the maximum power. So then we went to look into it very deeply. You can see this is the 5 different power cap. This is the configuration that gave the best configuration in this power cap, so best execution time. This is the configuration that's the default execution time in that power cap, and also this is the execution time that gives without any power cap, so without any throttling or anything. So maximum possible frequency you're using for the processor. This is the execution time for that. And if you look at that, you can see is that in all different 5 power caps, you can save, choosing the best configuration, you can save a lot of performance. You can increase a lot of performance of the different kernels. Now, here's a really interesting fact is that if you look into this 2 part, is that this is a 115 watt, this is a 70 watt power cap. So previously we have the notion is that, okay, if you increase the frequency of the processor, well, if you don't get any performance improvement, well, you will not lose it. But here we can see is that in 70 watt, we are actually getting the best performance for this kernel at 70 watt. And we assume due to some I/O issue, this might be happening. So you can see is that the best configuration for a certain kernel is not the best, like maximum frequency of a processor. So this is the kind of, so what we're currently trying to do is that coming up with a model so that we can model this behavior and choose the best configurations when an unknown application comes in. So it's easy to do like over and over for a known application, but when an unknown application comes in, we can do that so that based on a model. There have been some other works that's being done in my lab by some of my other colleagues. One of the work is that how much this affects the power consumption of DRAM. Can we change the power consumption of DRAM based on this configuration selection? So this one chooses, so we did these experiments on stream benchmark, and here you can see the impact of weight policy, number of threads, and process bind. In the number of threads as expected, so if you use more number of threads, usually the power will be more power will be used because more cores are accessing the same memory. On the other hand, the more important thing is that here is the data process bind, or more like the thread affinity. If you choose your thread affinity really well, you can save the power consumption as the green line in that area. You can see the green line is very small compared to all of them. So that means, and false is the default, so red one is the default strategy for OpenMP. So you can see that you can save a lot of power, even in DRAM, if you choose your configuration very well, or that's the thing. And one of my colleagues is also working on task-based, so how does it affect the energy consumption in task-based application? So what he did is that he experimented on Barcelona OpenMP task, two applications from that, the ETS and floor plan. You can see, so what he did is that initially we looked into the overall power energy consumption. He decided, okay, we know that overall energy consumption is a really big issue, but most of the time the energy consumption affects is the different OpenMP events, like how many time are you waiting in the barrier, so how much energy are you consuming when you're in the barrier. So you can see that based on the different scheduling policy, the energy consumption actually varies a lot. And also choosing the different number of threads doesn't really make is that if you use max number of threads, it will be maximum energy consumption. So here we can also see is that choosing the configuration intelligently can help the performance and energy consumption of an application, like whole OpenMP application. Like it can improve a lot of performance and energy. So here's some of the ongoing work we've been doing is that we're planning to adapt this model to a dynamically, so that if a new application comes in, we can do the dynamic adaptation without the users any input. So what will happen is that the user will give their code, it will run just like any code, but they will get a lot of performance improvement. We're actually working on, so our initial work we have presented is mainly based on OpenUH compiler. Now we're actually looking into different OpenMP runtime because based on different implementation, things may vary, the model may vary. So to create the model, we're looking into different OpenMP runtime, OpenUH, GCC, and also Intel runtime. And also, as we know that different architecture also has different way to handle things. So we're also looking into different architectures, into Sandy Bridge and also IBM PowerEdge. Now, some of the future works, so what can we go in the future? Well, some of the future works, as you saw, that most of the configuration we selected, it was a discrete configurations, but these configurations are not really discrete. They can, so for scheduling, for chunk sizes we use 7 distinct configurations, but they can go from 1, 2, 3, so they're more like a continuous configuration. So what we can do is that we can actually make a more concrete model for this configuration selection. And we didn't look into DRAM capping yet, so we're planning also to look into that. How does it affect the performance if we cap the DRAM power? And also we can use some other energy efficient strategies like DPFS or concurrency throttling or frequency modulation. And definitely, last but not the least, because at the end we want it to run in a bigger environment. So definitely we had to combine it with a distributed programming model, such as MPI. So this was mainly my talk. So I decided, I tried to give an overview that what is the main reason for OpenMP application performance, like how can we improve the OpenMP application performance. We given the factors and also show some experimental results. We also show some what can we do in the future. So please, if you have any question, please.